Recording in progress.
That's okay. So good evening, everyone. Today's lecture will be held by Juan Manuel López Medel from ICMAT, who will talk about the
component and transitivity.
The connected components and transitivity. So the floor is yours.
Thank you, Oscar, for the presentation. As Oscar said, we are going to talk about connected components and transitivity. But first, we are going to start with two results of the, that are consequence of the previous lecture. We are going to review. Well, the first corollary said that if we have a Lie groupoid, for each x in M, the target map in X that goes from dx to M is of constant length. And the second corollary will say that if we also have a Lie groupoid for all xy in M, G sub xy is a closed manifold, well, closed submanifold, closed embedded.
Sorry, could you write bigger letters?
Okay, sorry. Well, G sub x super y is a closed embedded submanifold of Gx, Gy, and G. In particular, each vertex group Gxx is a digit. Well, these results are consequences of the last proposition of the previous lecture that it was given by Asier, and the proof of this corollary is in the lecture notes, so you can check in there the proofs that are not very hard. Well, also in the end of the lecture, when we talk about transitivity, we are going to refer to these two corollary. Well, now we follow with a proposition about the tangent space. The proposition said that if we have a Lie group and a diffeomorphism phi from U to V, diffeomorphism from U V, bueno, aquí se ve a subset of G open and F from U to V a diffeomorphism from U is the imaging of U by the target map to B, that is the same, the image such that the next composition happens. So, well, phi compound with source is equal to target compound with F. Phi compound with target is equal to target compound with F. And phi H equal phi G H. And obviously GH are composable. G is in U and GH is also in U. Well, in that condition, the proposition said that the diffeomorphism phi is a restriction of the left translation map. Then phi restricting of L sigma. Okay. So let's start with the proof. For x in E, G in U x, we define sigma of x by C of J, the inverse of J. Define it is well defined. Okay. Sign the target map from U to U is a submersion. Sigma is smooth. And then it's a local bisection. Okay. On U with okay, that makes that L sigma of G is equal to phi of G with G in U. And we conclude that phi is the restriction of the left translation. Okay. Well, now we're going to say that the section.
That's the proof.
We are going to talk now about the structure of pseudo group of a local bisection. So, for a general Lie group G, we will treat the set of local bisections. Well, the set of local bisections as a structure of pseudogroup with the composition law, well, with the law composition star given by tau star with sigma of x equal tau e with sigma in is a bisection V and a bisection. Well, so we will refer to the set of all local bisection as the pseudogroup of local bisection with this composition, with this low composition, and will be denoted by bisection log of V. That's for the local bisection. Okay, also we can define morphisms of local bisection as a induced morphism of groups and pseudogroup. Group for the bisection and pseudogroup for the local bisection. As I said previously, you can see all the details of this result and definition in the lecture note that will be available soon. Well, now a theorem. That's it. If we have a Lie groupoid kappa de multiplication map if we have x vector field of TGE and y in THG such that the f of x, sorry, not f, is x equals the tau of y equals omega, then x bullet y is equal to the kappa xy equals the sigma y plus the tau x minus t sigma t tau omega, where sigma tau are any bisection that could be local, but well, bisection of G for which sigma source G equals G and tau is 8 equals 8. Okay. So let's go with the proof. The proof will be done in two parts. The first part is for, we suppose, T equals on M for M, and then we are going to do the general case. Okay, so we have in this case that x minus T1 Ts of x.
Sorry, Manuel, but what is chi here?
Chi in here it is the local bisection, I think, the bisection.
Okay. So maybe sigma or tau. Maybe one of those. Or
Yeah. Oh, sorry.
okay.
Sigma. Yeah.
Okay. Thank you.
No, thank you. Yeah. Sigma equals the trivial bisection. Minus T. Well, this is defined and is annulled. Is annulled by T of S. So x minus T1 Ts x bullet 0M is defined and we can write x bullet y is equal to x minus T1 Ts x dot O M T1 bullet y. Okay.
So 0 maybe is 0 h.
Yeah, exactly.
That you refer to the zero vector of the.
Yeah.
Okay.
Yeah, if not n is
Okay.
thank you. Now we are going to use identity that we saw in a previous lecture, and the equality is this. Is for the multiplication map kappa T8 T X. Okay, we use this. That and remembering this thing, yeah. T1 T1 is an identity in T we have the equality x bullet y is equal to okay. So using this identity of a previous lecture, using this is an identity in the tangent space of G, we get this equality for the case of the identity bisection. And now we are going to consider the general case. Okay, so for this case, first we have the translation on the is equal to G. And now denoting theta by T of L minus 1 G of X sin L sigma convenes with the source map we apply that equality to get the bullet of zeta and y. We get that T G zeta minus T1 Ts zeta plus 1. Now Sg is the restriction to GTH to GSH of this map. Also, X bullet y is equal to TL sigma Z bullet y equal to sin kappa compound with kappa. And this one may name of the proof. Okay. Well, as I said before, the theorem gives us a multiplicative structure of the structure of the TG, the tangent of T. Well, and in particular, I'm going to write an expression when, well, if X in the tangent space and sigma is a local bisection with sigma S G equal 0, then so T1 T2 minus okay. So at this point, the section of bisection in Mackenzie's book will be complete. And now we are going to start with the fifth part of, well, fifth subchapter of the book. Well, that is components and transitivity. Well, our first, well, one of our objectives is this: extend two elementary facts about topological group. The first is that the component of identity is a subgroup. And the second fact that the subgroupoid is, well, the subgroup is generated by any neighborhood of the identity. So we are going to expand this two result to the groupoid. Well, we are going to start with the proposition, the groupoid. For each element x in M, P sub x denotes the connectedness component of the arrow 1x in G. Then G6 equals CP equals unit of this is a widely subgroupoid of G on the identity component subgroupoid. Okay, so we are going to start the proof of the proposition the first thing that we are going to say is that is y. Then we are going to see that it has it verifies the multiplication and inversion action, and then the differential structure. Yeah. By definition, every arrow 1x with x in it is contained in the set C. So is y. Now we're going to say that C is closed under the multiplication, so we take G in this set and 8 in this one, and we consider the multiplication is in okay, because G goes from C, so Gy to G set is a diffeomorphic. It must component to component. Connected component to connected component. And because G is equal to the image of the arrow of y under this map is included in this set. We have that the next intersection C is is not void. Also, CX equals and HG in CX. Prove that C is closed for multiplication. What? Under multiplication. Now, taking G and C, we have, I think this is a signal. What? So the image of the set under the right translation under the inverse element of D is equal to 0, and hence we got that the inverse is also in that set. So C is closed and the inversion. And for last, we are going to prove the differential structure. So we take a tubular neighborhood of the set 1n. Well, be a tubular for 1 sub n. Now regard n as a vector bundle. Over m with its zero section identified with 1 from n to g. Then this tubular neighborhood is included in our set C. Now C sub x are lift of the population defined by the alpha g. That this is okay. And C is the union of the integral manifolds of T and G with the open set N. And C is open, so we can now conclude that C is a subgroupoid of G. Okay. It is also implicitly said in the proof that the T fibers C super Y are the identity components of the T fibers G super Y of G. Well, you can see more detail in the lecture note.
I know what is alpha. Yeah, sorry. What is alpha?
Sorry, alpha is yes, I think.
Yes.
Is the source.
Okay.
Sorry.
Also in care of the
Oh,
alpha.
yeah. Thank you. Sorry. Yeah, exactly. All the alpha is S. Thank you. Well, let's continue with the proposition. That said that the identity component is open in G as before. Now we prove that C is open. So okay, let's make the proof. Let P be a match between this product to you, be a chart for the foliation in this by PSD where you intersect neighbourhood and the image of the zero section is equal to the intersection. Then U is contained in C. Now we take the union of U of all the U's of that type. We obtain an open neighborhood of 1n in G, which is contained in G. Sorry, in G, no, in C. So C is the union of these leaves of the foliation which intersect the open neighborhood so C is open. Okay. Well, now we continue with last proposition that said that if we have G locally trivial Lie groupoid on a connected base M, then the set C equal to C omega is also locally trivial.
Sorry, camera doesn't follow you. Okay, yeah.
Thank you. Okay, so the last proposition I wrote is that if we have a locally trivial Lie group on a connected base M, the set C is also locally trivial. And we are going to skip this proof, but you can see in the lecture note. Well, in general, if a Lie groupoid has a subgroupoid which is locally trivial, the ambient subgroupoid itself must be locally trivial. That's what is said in the proposition. And now we are going to talk. If we have a principal bundle, in G, principal bundle on a connected base, any component PO of P defined as set H, that is the element of G that this component invariant. We can see that H is a open subgroup of G Also, we have that the restriction of the map phi to that component is surjective so it remains a surjective submersion since P0 is open in P0 in P. Okay. Furthermore, O times C2 P0 remains a free action, and its vortices are equal to the fibers of P0. And then we can define that P0, M, H, and the map pi 0 is a connected reduction of the principal argument. And now we are going to do an example. we take P as R times with the semi-direct product. N2 equals N1 plus N2 minus 1 N2. Okay. Let G act on P to the right by S P M P M. Okay. We consider P2M equals S1 with the XP equals to well, we have that P and G prime is a principal bundle and the component of P through 0 through 0, 0 is R times 0. In this case, H is equal to Z times 0 and the bundle, well, the bundle P0 and H can be identified with the cover S1 set. Okay. P and G is the pullback of the universal cover. R2 kg of the grain butter around this mark. You see? By L2 to L3 with, sorry. Okay. Well, let's go on with a proposition. We have a Reading Groupoid, and we have that U is a symmetric set. I remember that this is that U is equal to U minus 1, and that the set 1 sub n is contained in U. So U is a symmetric set that each U sub n is open in U sub n. Then the subgroup H generated by U has open has X open in with X for X in N. Well, before the proof, a set U that is symmetric satisfying this condition of this proposition is called the condition of this proposition is called a symmetric S neighborhood of 1n in D. And the proof of this result, I'm going to skip it. You have
Yeah,
it.
sorry, camera doesn't follow you again.
Yeah, this proposition that I'm not going to prove, but maybe at the end of the session. Only that if we have a set satisfying the condition of this proposition is called a symmetric S neighborhood of 1n in G. Okay. Well, now another proposition. Another Reading Groupoid with 8 y, the subgroupoid of each hx is open in Gx with x in n, then each hx is also closed in GX. Okay. To end with the component, a last proposition. G groupoid over M, and U symmetric as neighborhood, as the definition I write before. Then U generate the identity component subgroupoid. And with this proposition, we end the two objectives that I wanted when we started this section. That I said we want to see that the component of identity should be a subgroupoid. We prove it that, and then with this proposition, we prove that the identity the identity component generate this component, this connected component. And now we are going to follow with transitivity. Well, as you know, G over M is transitive if the the anchor map TS is surjective. Well, the other extreme case of this is given by this definition, that is G over G, the groupoid is totally intransitive if the image of TS is the base subgroupoid delta M of M. Okay. The image of the anchor is an equivalent relation on M. And we denote these classes of X in N by OX, that this is equal to beta, sub X, and this is the transitivity orbit or component. And we sometimes omit the word transitivity and we just only call it a component. We also know that the orbit of X is equal to the image of this X under the tangent of this. Now we follow with two examples. The first one is that the transitivity component of a fundamental groupoid are the connectedness component of N. And the transitivity component or of an action groupoid and are the orbits of the action. Well, also a Lie group by bundle is a Lie groupoid. Well, not sorry, groupoid, not even that. A Lie groupoid by bundle is a totally intransitive Lie groupoid. Groups are both transitive and totally intransitive. Well, yeah. Well, for a groupoid, is restriction to the orbit GO is a transitive subgroupoid. Of G can be regarded as the disjoint unit of the transitive subgroupoid. Subgroupoid G0 as the orbits right. Well, in the case of Lie groupoids, the smooth structure cannot be obtained so simple as in the case of Lie groupoid. Well, now, if we have a Lie groupoid for each x in M, the orbit of X is a submanifold of M. Well, I'm going to skip also the proof of this theorem because I want to complete all the result, but the proof is in the lecture note. Yes, let's continue with some remarks. For example, well, in particular, we have that this set is a principal bundle. Is also there, that well, since the target map is of constant drag, this was the first corollary that I wrote in the blackboard that I said we are going to use it before. The first one was that this map is of constant drag. So this is constant drag implies that the division map is also of constant drag. So this map gx on dx over dx to g is an injective of constant drag and therefore is an inversion. Thus, G O X is a submanifold of G. And this was the proof of the last theorem of the session and not the last result that said that the Lie groupoid or orbit on M. Then there is a manifold structure on G, which it is a submanifold of G and a G groupoid on O. G O is locally trivial. Okay, this gives us some corollary. A transitive Reading Groupoid is locally trivial. And also Reading Groupoid over M and this not is of constant rank and G is locally trivial if and only if delta X is a surjective submersion. Okay, and now we are going to finish with a proposition okay. If we have a groupoid, we have also a submersion such that beta times beta and the ICMAT are transversal, then GSS with its submanifold structure is a least subgroupoid of G. Okay, so a submanifold satisfying this condition is said to be transversal to G. So maybe I'm going to write it. Yeah. is said to be transversal, sorry, transversal to G. Okay. And with that,
Sorry, why are you requiring that the inclusion is submersion?
yeah, I
think
no,
it's just
not
the
necessary.
submanifold.
Yeah, because it's just needed to be submanifold, yeah, but not actually, yeah. No,
Okay,
yeah,
thank you.
thank you. Sorry. Yeah, the only requirement is to be submanifold, not, yeah. Thank you. Yeah, submanifold satisfying that condition is said to be transversal to G. And with that, I conclude the lecture.
Okay. So thank you, Manolo, for the talk. So is there any remark or comment? Question? Okay, so I have one. You said that precisely that Lie groups are precisely Lie groupoids, such that they are both transitive and totally intransitive, right? I think that the converse also holds, right? Because if the diagonal of the manifold is equal to the Cartesian product, then you only have one element, and you are saying that the anchor of the Lie groupoid is surjective, so you only have one base point, right?
Yeah.
Okay, so
yeah, I think. Yeah, I still think.
Okay, is there any more comment?
See,
I have
yeah,
one.
yeah.
So you probably know already some theorems about, let's say, orbits of actions of groups, Lie groups, on manifolds. That in some situations they are actually embedded in manifolds. And I was wondering, I know that this is nothing that we've seen so far, in the book, but I was wondering if you know if that it would be true for some actions of groupoids. So say that, for example, if the orbit is locally closed in M, then it also has to be an embedded manifold, just as for Lie groups. If you don't know, I mean, I'm asking also everyone, so. Okay.
So you're saying like these locally closed results for Lie groups, right?
Yeah.
We know that. So you're asking that if we have a locally closed, you're saying orbit of a Lie groupoid, then the Lie groupoid is, well, the orbit is
a manifold.
embedded submanifold.
I expect that to be true, but I wonder if anyone knows.
I don't know, but is there like anyone in the audience who knows?
Like the action of a groupoid on a manifold.
I mean the orbit of a groupoid in this case. So.
This one, this orbit, right?
Yes. So this. Yes.
But what is the analog in a group then?
I would be for I guess that you're looking at the. Oh yeah, right. Okay.
Yeah, I think it is.
Okay.
If you mean the action of a group on a manifold, then the analog is the action of a groupoid.
Yes,
on
it
a
would be
manifold.
okay. I'm thinking of the I guess an orbit of an action groupoid then specifically. Yes. So. Yes.
That's the next section.
Okay.
The next section will be
Of the
about
book.
action.
I mean.
Yeah, but I mean it also would be the orbit of an action groupoid.
But of any groupoid of
I was asking of the orbit of a given groupoid, but then also you could give the same question for the action of a groupoid on a manifold, which is more complicated, and it is the next question. But also the situation for actions of Lie groups is a particular case of this because there are the action groupoids. So
yeah, for sure.
Okay.
Yeah. I think maybe in the next section we can discuss about that because we will talk about action.
Okay.
Okay, so thank you everyone for coming and see you next week. Okay.
See you.
See you.
Where do we stop recording?
Yeah.
Here.
Sí, creo que.
Okay.